Hey guys, can I get a sound check?
You were breaking up, but we do hear you.
Okay, thanks. How does this sound? This is still breaking up?
All right, sound looks good, but now your camera's blurry.
What's that?
Sound is good, but your camera's blurry now.
Uh, well, let's try to work with this because I was trying to share a video with you guys. So later on, so let's try to work with this, and then if it all fails, um, we'll try. I'll just try having my audio with my cell phone. So guys, let's see. I guess I'll wait for another minute or so. Join in. Okay. Yes, we have 23 participants. Okay, guys, so we're gonna have a quiz the first thing today. Oh pain, oh joy. So if you guys go to the files section of Canvas, you should be able to see a PDF called Quiz 0. Let me do a screen share. Let's see. Do you guys see it on my desktop?
Yes.
Yeah.
Okay. So let me just describe. It's got two problems. And notice that the first one is asking for the solution is asking for the ratio of V out. I don't know if you guys can see my cursor, but it's this voltage across these two nodes in relation to the V in here. And basically, you're supposed to use Kirchhoff's voltage law and Kirchhoff's current law. There's a little hint here. I don't know how good of a hint it is, but that's one. And two is similar, but it's basically the voltage gain of this amp. And here, notice that output is down here across this resistor, from the resistor to the ground, and the input is here. So why don't you guys take, let's say, how much do you guys think you need for this? Let's give you guys 30 minutes. So to try to solve these things. So why don't you guys go ahead and take a shot at these guys and then hang on to your tests. I'll at minute 30, we'll basically at 6, we'll start talking about what to do with it. Okay. Any questions? Okay, guys, go ahead. Good luck.
Good evening, sir. Sorry, I just joined the class. Are we having a quiz right now?
Yeah, it's on the canvas under files.
Okay, thank you.
Sure. Okay, guys. How did that go?
Okay.
Okay. I like okay is good. Well, okay, guys. So why don't you guys hang on to your test? So, like I mentioned, this is not going to be a graded quiz. This was to sort of get you guys thinking about whether you need to refresh your basic sort of circuit analysis knowledge that you need for this class. How you're doing with that. So let's solve the problems. So go through. I'll work through the problems with you guys, and then you can kind of look through how you did. And the idea is just basically like if you breeze through it, fantastic. I mean, this is kind of the level of circuit analysis you need for this class, and the level of math, pretty easy, relatively speaking, if you have the background. And if you don't, it just means you need to go refresh kind of chapter 1, get reacquainted with the concept of Kirchhoff's voltage laws, Kirchhoff's current laws. They're all pretty, basic stuff, but, sometimes you need to go refresh your memory about what those are, because we'll be using those basically 2 basic elements for the class. So, okay, so let's start with this first problem, and then I'll tell you guys a little bit about, so this ends up that's sort of a leading quiz, because these exact circuits are kind of, as you'll see later, probably in week 3 or 4 or something like that, or like your model, a simplified model of what a transistor looks like and what a transistor with a gain looks like. So let's look at the first one. So let's see. There's this resistor, R sub pi, and all these things hopefully will start being meaningful. And there's the voltage across the resistors is called V sub pi. And then we have a current source here. It's I1, and the value of that current source is G sub M V sub pi. So this makes this current source well, let me put it here. This makes this current source what's called a voltage controlled current source. Okay, so just like a resistor has a resistor has this relationship. There's a voltage, and then there's a current across it. So V is equal to IR for a resistor. I always have to write this down. So so I is equal to V over R. Okay, so basically we're going to have like a line here, and the slope of this line is 1 over R. That's the definition of a resistor. Everybody good with that? It's like real basic concept. So for a current source, the relationship between voltage and current. So this is also, you're going to see a lot of these voltage versus current curves in this class. So a relationship between a voltage and a current in a current source is, in a typical current source, would be, no matter what you do with with this, say, current source, and a typical symbol for a current source is either this, or you might see this or something like that, is no matter what voltage you put across this current source, so no matter how much you change the voltage across the current source, the current through the current source stays the same. So that's just a regular current source. So a voltage dependent current source means that there is another voltage somewhere else. So not the voltage across the current source, but another voltage somewhere else. In this case, it's this voltage across this resistor, V sub pi. And if that changes, so if I draw, let me do different lines. If I have this, V sub pi being a value of 1 volt, the current will end up down here, but it doesn't change with this voltage. Notice it's still a straight line with this voltage across it, but it'll be a certain value. And if I change the voltage across V sub pi, make it higher, it'll be some other. So V sub pi is equal to, these are just sort of like, just to give you guys an idea. V sub pi is, make V sub pi higher, I can make that current go higher, but still this current is not going to be a function of the voltage across this node. It's a function of the voltage across that node. And that ratio in this particular case is this thing called G sub m. And we'll see later why that's called G sub m, et cetera. It'll be meaningful later. Okay, so that's a voltage controlled current source. Okay, any questions so far? Current source, voltage source, etc. I mean, sorry, resistor, current source. Everybody's good with that? This is like, we won't have too many complicated circuit elements, but we'll have those. Okay, we've got another resistor here, R sub L. And then we have our output voltage across this node. Again, the current here is V sub out over R sub out, just like you see here. Okay, and then there's an input, Vn. Okay, so the problem asks for the ratio of, so what's V out over Vn. Okay, so let's sort that out. So let's see. So, the first thing to notice is, so you have this Kirchhoff's current law. And Kirchhoff's current law basically says that the sum total of currents going in or out of a node have to be 0, meaning that there's a current I1. So if you look at this node V out, there's a current I1 going this way, right? The current's going this way. And there's a current going this way. Let's call that current I R sub L. Okay, it's saying that the sum of those currents has to be the current sort of going this way into V out. Or, yeah, and so there is no current V out, right? This is just an open circuit here. There's no load here. Okay, so basically what it means is that this current has to equal to this current, because this plus this will equal to this, which is 0. So let me just write that down. So this is KVL at V out node. Sorry, KCL. This is Kirchhoff's current law. So it's basically saying I1 plus I sub RL is equal to I V out, which is 0. Okay, so that's Kirchhoff's current law at this node. Okay, now let's start plugging in numbers for this. So I1 is this guy, which is G sub M V sub pi. So I'm just going to write that down. And I at R sub L is just V out over R sub L. So these two are equal to 0. Okay, so now let's pause here for a second and look at this v sub pi. We don't have any v in here, so it'd be good to get this v sub pi in terms of vn because it's sitting here and it's related to vn. And if you look at Kirchhoff's voltage laws, it says that if you go around a loop, so if you start from here and go all the way around, the sum of those voltages has to be equal to 0. Okay, so basically Vn, and if I'm starting here, this is minus plus, right? Then I'm seeing plus minus, so Vn minus, let's say plus minus v sub pi is equal to 0. Okay, so starting from here, I got Vn, I'm subtracting this v sub pi or adding the negative value v sub pi. I'm coming back to Vn, that's got to be equal to 0, meaning that Vn is equal to v sub pi. Okay, so I'm going to write that down here. So Vn is equal to v sub pi.
I have a question real quick.
Yeah.
So when you did KCL, wouldn't the currents leaving the node be negative?
Yeah, it just depends on the sign. So I think if you want to say like minus I sub 1 minus R sub L is minus I sub out, you could do that too.
Okay.
Yeah. So I think strictly speaking, you're correct. Thanks, Ellis. Okay, so I'm going to plug in this Vn into this v sub pi. So I'm going to like, once we have negatives everywhere, I'll just make it all positive again so that we don't have to carry the negative. So this ends up being G sub m, V sub n plus V out over R sub L is equal to 0. Or just rearranging everything, V out over R sub L is equal to minus G sub m Vn. And we're basically, the problem asks us to figure out the ratio of V out over Vn. That's minus G sub m R sub L. Okay. So that's the answer to the first problem. Any questions about that? Anybody have any problems with it? Everybody got it okay? Nobody's owning up to anything? Okay, guys. So anyway, so that's a simple example of Kirchhoff's current law, Kirchhoff's voltage law. Okay, so and one thing to sort of, again, we'll talk about this later in the transistor section, but this ratio of output voltage. So let's say if I just looked at this thing, if I was going to look at this thing as like a black box where I had a input voltage and then I had a output voltage. In this case, they're both referred to ground. Okay, if I had such a thing, this ratio of output to input would also be this thing called a gain. It's just called gain. So, and then this is sort of a pull-on circuit block. Okay, so that's, again, that's called a voltage gain. And for example, think about if you had a microphone as an example, we'll see over and over again because it's easy to visualize. The microphone has, there's like a mechanical membrane there in the microphone. It's picking up the vibrations for from the air, from my voice or whatever. So it's getting, so if this was a microphone or something like that, I would buy a microphone. It's getting a real small signal, just because it turns out that this mechanical membrane can't create a really large signal value coming out. And then, you may just want to be able to adjust that, the loudness from the microphone. So it's really nice. What you want to do is put that signal into a circuit block that has gain, so you can amplify that. So you can make V out. You can make V out much larger than V in, for example. Or let's say you want to attenuate that signal for some reason. It's too loud coming out and you want to reduce the audio signal. And so you want to reduce the ratio of V out to V in. And that's called attenuation, although they're both called the voltage gain, the definition. But one of them is amplifying and the other one is attenuating. Okay. In this case, the gain is negative, and you'll see that over and over again in our circuits. The sign is something that is just the direction of where things are going. You're still amplifying the signal. You're just inverting it, and we'll see how that doesn't really matter. Once you kind of figure out how to deal with it, you're able to deal with it. Okay. Okay. Any questions, guys? No. Okay.
I got a
So
question.
yeah, go ahead.
So for the gain to be negative, does that kind of mean that it's supplying power, like voltage or something, or does it not?
All it means is, like, let me just draw something. Like, let's say, so I'm gonna now draw so let's say I'm gonna put this now. Have you guys all used oscilloscopes and stuff before? You haven't used it, Parker?
A little bit.
I mean,
Okay, so that's just the instrument that you sort of plug, put on your circuits, and you see.
I'm familiar with it, but my lab for 1101 was online.
Okay, so but I mean, just as a general concept, you have, let's say typically you have a voltage, and then it's a function of time. So if you had a sinusoidal input, okay, in the case of, let's say you just have, this is your input, and this is kind of the trace you were seeing, so this is your VN. And if you had a positive gain value, your V out might look like this.
Okay.
This is really badly done, but you get the idea. And if you had a negative gain, your V out would look like this. It'd just be still gained up, but it would have the opposite sign as your input.
Okay.
So the fact that it's negative, in both cases, you're getting current, etc., you're getting power from the power supply, is just the sign is inverted between the input and the output.
Okay. Cool.
So, a lot of times, like, let's say in an audio circuit, video circuit, whatever, there's multiple gain stages. And what people do, if you don't want an inverting gain stage, is you'll put a even number of, as you'll see, for whatever reason, I don't know if there's some fundamental reason or not, but transistor circuits like to give you negative gain because of negative feedback, etc. So if you want a positive gain, you would put two stages. Each of them will have a negative gain, and in total, they'll give you a positive gain at the output. And if you want a negative gain, you'll put in an odd number stages, 1 through whatever. Okay, so it just means that the sign is reversed from the input to the output. Okay, and that'll take a long time before it starts making sense. Why that's like a. Also, it's honestly, it's a benefit, but anyway, it'll become clear a few years from now, maybe next year for you guys, or next semester. Okay. Second problem. This is more math, more involved. Let me just draw this guy. Okay, we have the same R pi circuit with V sub pi across it. And we have I1. This is again this voltage controlled current source. Okay. And then we have this R sub E. And in this case, we also want V out. Question is, what is V out over Vn in this case as well? Okay. So now we have a similar kind of issue. Okay, so that we want to basically here, notice that our V out is down here. Whoops. V out is down here. And Vn is over here. Okay, so now with we have, if we look at KCL, we look at this node. Okay, we have this current I R sub pi going in here. Okay, we have this current I sub 1 going here. And then we have this current I sub RE coming out of that node. Okay. So I was gonna write that KCL equation for there. And so as Elvis corrected me, we got so plus I sub R sub pi plus I1 minus I sub RE. So notice R sub BE is coming out of that node, the way I drew it, that's equal to 0, or IRE is equal to R sub pi plus I sub 1. Okay, so now let's try to figure out the values. Now remember we want V out and V in. So we're gonna try to figure out, start populating this somehow in terms of V out and V in. So the very tempting thing to do here is to say, oh, okay, well, I remember this V sub pi from the last problem, right? This V sub pi from the last problem was just Vn. So this is, again, very tempting thing to do. It's incorrect. But you say like, oh, I of R pi is V sub pi over, R sub pi. That one's correct, right? But, oh, that's equal to Vn over R sub pi, okay, which is incorrect. Because notice here, when you're doing KVL, so this is ground. This is ground. So that means, these two nodes are connected together. So the KVL here is this Vn plus the negative value of V sub pi plus the negative value of V out has to be equal to 0. So it's basically, this is your total loop around here. So in fact, Vn, if you do KVL on this loop, so loop, I'll call that loop 1, okay, is Vn plus minus V sub pi plus minus V sub out is equal to 0. Okay, or V sub pi is V sub in minus V sub out. Okay, And the current, so the current R sub pi is V sub pi over R sub pi. So I sub pi, I of R sub pi, sorry, is V in minus V out over R sub pi. Okay, that's this guy. Okay, and then I sub 1, which is this dude here. So that's this guy. So this guy is I1 is G sub M V sub pi from here, right? And so V sub pi, you see, we have that. So I1 is G sub M V in minus V out.
Can you explain KVL loop 1 again?
The KVL?
Yeah.
Okay, so what KVL says is when you go around any kind of a circuit loop, the sum total of the voltage when you get back to your same point is going to have to be 0. Okay, so this guy is connected to ground. This guy is connected to ground. So the first thing to observe is really, this is shorthand for the fact that these two nodes are connected together and to the same thing. Okay, so you have this voltage across this guy, you have this voltage across this guy, and this voltage across this guy. So the sum of these voltages has to equal to 0. Okay, but because the directions of this Vn is defined plus and minus, and then V pi is is defined as plus minus, it's sort of the reverse direction as Vn. If V sub pi was defined as at minus plus, then you just add it to the end, same V out. So what I would do here is say Vn, this is the KVL equation, plus the negative value of V sub pi, because of the way the V sub pi is defined inversely to Vn, plus the negative value of V sub out, because again, it's defined plus minus compared to, it's reversed with V sub in, minus V sub out, oops. The sum of all these has to equal to 0. So that's the equation for the KVL across this loop.
Okay, yeah, I was just confused about the signs, but you explained that, so thank you.
Okay, yeah. So
Another
this is,
question.
yeah, go ahead.
So how'd you get the directions of the currents? Was it for the voltage drops?
Yeah, I mean, you could go either way. So this current, sorry, this current is like the direction of the arrow through a current source as you saw it here, tells you
Yeah.
what direction it goes. I usually define the current from a resistor from going from positive to negative node. So that's why I defined the directions, just coming
Yes.
from the,
Then another question. So there's a node between V in and R pi. Does that mean the currents leave that node, both of them?
so you're saying this node here,
Yeah.
and what's your question here?
So would currents be leaving both sides? Because wouldn't that not?
Well, the current I sub R, like the current sort of here is going to have to be whatever current comes from here has the same current has to leave through. Does that make sense?
Okay.
So if this is I sub R sub, like if this is I R sub pi, then the current coming out of this guy also has to be I sub R pi. So
Okay.
strictly speaking, yeah, you would have to, you want to analyze it, but it's really the same current. There's no summing of
Okay.
current.
Okay.
Make sense?
I think what may help some people is just redrawing the circuit with only showing one ground. That way they could actually see the full connected loops.
Oh, I see what you're saying. So I mean, connect all these guys.
Yeah, I think just connecting them will kind of help some of the other people help visualize it.
Yeah. Yeah. Okay. The thing is, I also, great. Okay, thanks for, yeah, that can get confusing. The thing is, we also want you guys to start getting, it gets really cumbersome to do that when you start, our circuits are going to get more complex. So it's good for you guys to like start getting used to seeing that when you have grounds, it means they're connected to the same thing. But I think you're making a good point. That is usually confusing, is where the grounds go. But like Brandon said, basically all these points are connected together. So if you're looking at, say, you could be looking at, well, there's no loop here because there's no, strictly speaking, this voltage doesn't change across this. So really only kind of have one KVL that you can worry about. But I think between all of you guys that are asking questions and raising points, etc., is the important thing to realize when you're solving these type of equations. And bad news is there's lots of them to solve in this class. It's easy to mix signs up, directions. So be sort of, especially beginning, maybe as you get more and more, by week 10 or 11, you might start being able to take some shortcuts as you get more used to figuring out directions of currents and voltages. But try to be really rigorous, as stupid as this stuff is. Just like draw stuff out, make sure you've got your signs right. Just take it sort of step by step. I have a tendency just to jump to conclusion, oh, this voltage is equal to that, whatever. And that makes me screw up signs here and there, which is could end up being catastrophic when you're trying to solve a problem. So just be systematic, disciplined about the way you guys look at the summing of these voltages across these nodes and looking at currents, etc. It's just really simple. If you look at KVL or KCL, it's two extremely simple rules, but it does, create a lot of complex situations. And also when you're looking at these components, right? I mean, so far we have, resistors, which are pretty simple concepts. It's a pretty simple equation across a resistor, like I wrote. Current source, really simple equation for a current source. Voltage sources, simple equations, etc. So, but you just have to be rigorous the way you look at it. So I think that's one thing we're to remember. Okay, so any other questions, guys? Otherwise, I'll keep going with the solution. Okay, so and then so I'm going to plug these guys into this I sub RE. So I sub RE is V out over R sub E. Okay, so this is V out over R sub E. So that's this guy is equal to IR pi is Vn minus V out over R sub pi. Right. Plus I sub 1 from here. Whoops. Is GM Vn minus V out. Okay, so now the good thing is we have everything in terms of, or at least we have V out and V in, which that's what we want to solve for. So the rest of this job is just to move stuff around to get things in the ratio of V out over V in. So let's remember, we want to find V out over V in. Okay, so the steps I took was just I multiplied both sides by R sub E. So and then multiplied stuff out. then started redistributing. This is just algebra, in which you can go wrong in as well. And I do often, so I'm trying to be careful here, make sure I follow my notes and then move the out. Move everything over here. And, just again, I'll go through each step I did. But it's probably boring for you guys. Let's see, 1 over r sub pi plus G7 r sub e over 1 plus 1 over plus G7 RE. And multiply both top and bottom by RE, R pi. So multiply by RE, R pi over RE, R pi, and then you basically gather stuff up and you end up with 1 plus G sub m R sub pi RE over sub pi plus 1 plus G sub m R sub pi over R. Okay, that's that ratio. Okay, any questions about that, guys? I was just, the rest of it was just algebra, trying to, get it in some format. You would have been okay. Anywhere, like if you had stopped, anywhere here or whatever, would have been fine in terms of getting graded or whatever. So that's that. So I think, again, lessons learned is KVL, KCL, do a bunch of, if you guys, again, if you had a problem with this, I think chapter 1, it's got a bunch of problems in the back. Try to do a few of those. Do I have solutions to that? I might have solutions. If I have, anyway, you can try, doing some of those, get used to it, and just, be careful with your simple algebra as the rest of it, I think. All right. Any questions? No? Okay. Anyway, if you did great, if you did good, great. If you didn't, don't be discouraged. It is painful, and God, over long breaks, I get rusty solving these things and start questioning yourself, but this just takes lots of practice to do the math. Okay, so guys, so that was the quiz as a starting point. And so I wanted to, I think one of the, I'm really worried about teaching this class. Again, I'm like, this is, I don't know, 4th or 5th semester I'm teaching this class. But just given my own history of my level of understanding of why the heck I was taking this class when I did, when I was your age, and sophomore in undergrad, and and then how long it took me to get a big picture idea. I'm going to try to give you guys kind of a big picture idea of what is this path you're going down with microelectronics. This is, this class is your first, baby step along this path. And you're going to have, many more semesters of that if you're doing electrical engineering and doing microelectronics. And so in this class, you're just kind of like figuring out some of the language, how this stuff's made. Again, real baby step stuff. But what I wanted to do was to show you guys where it sort of all is going. Okay. So I'm gonna do let me share. This will stop. You want to continue? Okay, I'm gonna stop sharing that. Okay, I'm gonna share this screen. Can you guys see the Wall Street Journal screen shared?
Yeah.
Okay.
Yep.
So I don't know if I told you guys this or not, but Wall Street Journal. So this is I'm gonna give you guys lots of pieces of unsolicited career advice during this semester, and one of them is to start sort of reading the Wall Street Journal on a real casual basis. You know, it's not just about, you know, if you're a stock investor or just in business. It's really the newspaper, the source for how the economy runs and how your life as a professional, what the overall business world means to you as a technology professional. There's great stuff on the home page, but then they have this literally great tech page. And lately there's been a lot of news about semiconductors. And this is a article that came out, what is it? It's updated August 23rd. It may have come out a few days ago. I don't know, about Intel getting this deal from the Pentagon. It's like a $2.2 billion deal to help them, upgrade their manufacturing capability in the U.S. As part of the worry that competition with China, et cetera, the U.S. doesn't have a good level of a good base in semiconductors anymore, as U.S. was a leading manufacturer in semiconductors, but it's no longer the case. So anyway, so this article is about there's lots of good stuff here, but I'm not going to go into that. Just, my advice is, a couple of times a week. You don't even have to read every article. Just sort of look through the front page, look for semiconductor stuff or stuff about tech, etc. But then, the thing I really wanted to show you guys was this video that they have embedded in it. Hopefully it'll work okay when I press play. But this is an 9 minute video that talks about how microelectronics are produced as of 2020, 2021, where we're at, and what the manufacturing site looks like. Some of you guys may be familiar with some of the shortages in semiconductors if you've tried to buy computers or GPUs or something lately, or cars even. So this talks about that, and I think it's a really good high level introduction to chips. That's another word for microelectronics, etc. So I'm going to hit play. I think I'm going to try to do closed circuit. Some of it is a little hard to follow, but hopefully you'll hear the audio here and we won't get an ad. Okay.
This chip controls your car, stores data about what you bought, and runs the software on your laptop. These chips have come to power our lives, and only a handful of fabrication plants or
are you guys getting that okay?
Yeah.
Okay, great.
labs in the world have the know-how and infrastructure to make them. So most of the chips are produced outside of the US, like at this fab in Singapore.
To build a fab is a big investment.
And now the world is running out of chips because companies can't make them fast enough.
When order really flooding in, we had to turn on every single piece of machine that we can find in the factory.
The pandemic rattled supply chains and led to a surge in demand for electronics when people were stuck at home. While a perfect storm of natural disasters, a fire at one of the world's leading auto chip makers, and the ongoing US-China trade war disrupted the production and distribution of semiconductors. This shortage has affected whether you can drive a Jeep off the lot or buy a new PlayStation 5. We visit one of the world's largest contract chip makers to see the complex process and why there's no quick fix to the supply crunch.
Chip usually takes about 2 to 3 months to make.
Daniel Rajkumar is a manufacturing manager at one of the fabs at Global Foundries. The American company is the third largest contract chip manufacturer in the world. Companies like Intel, AMD, and Bosch give some of their circuitry designs to Global Foundries. And then its fabs like this one in Singapore manufacture the chips.
Once we finish the fabrication of the circuitry, it has to go for testing, it has to go for repackaging.
Altogether, it could take as much as 6 months before a chip is ready to go into your tech. This long process starts here at the center of the fab called the clean room.
Before going into the clean room, we need to gown up.
Because chips can be as small as a fingernail and crammed with billions of components, they have to be handled with great care.
Any form of dust that falls onto the wafers, it will cause the chip to be defected. And then now we are able to go into the air shower.
Global Foundries says this clean room is 1,000 times cleaner than an operating room. And it also takes up a lot of space.
2 football field, that's how big it is. We have about 700 to 800 machines.
It's also yellow in here because chips are sensitive to UV rays, and this lighting has none of that.
This is always the first step.
The starting material for any chip is here in this room. These super thin discs are called wafers and made from silicon. Eventually, one of these will produce about 1,000 to 1,500 individual chips. But before it does, the wafer is placed in a special container.
We have the raw silicon. We are now trying to register this material and transfer it into our wafer carrier.
Each carrier can hold up to 25 wafers, and there are about 4,000 of these moving around the facility at one time.
We are also the source of particles when we go into the clean room.
So never once during manufacturing does the wafer come in contact with any of the workers.
We will bring the wafers directly to the machine, and in this foundry, basically 95% of all processing jobs is fully automated.
These raw wafers are cleaned before starting a process that Rajkumar describes as similar to making layered cake.
The main function of a diffusion furnace is basically to grow layers of oxide or to dip a nitride onto the silicon.
That creates a protective coating. Next is a layer that makes the wafer light sensitive, so it's ready for one of the most important steps called lithography.
This is the most expensive module in any wafer foundry. The number of lithography machines will define how many wafers you can produce in a month or a year.
One lithography machine can cost anywhere between $25 million to over $100 million. And that's because it's responsible for adding layers of the circuitry, basically electronic components like transistors and diodes that allow the chips to eventually store data or run apps.
What I'm holding here is basically a pattern design of a circuitry.
Inside this pink box is a photomask, which is like a glass stencil, and clients send these directly to Global Foundries. The lithography machine blasts UV light through the photomask and prints patterns on the wafer over and over again. The difference between an advanced chip for a 5G smartphone versus one for your credit card comes down to the type of wavelength that's used. Shorter wavelengths mean you can etch finer features and get more performance out of the chips. Some of these transistors are so small that they're measured in nanometers and compared to DNA strands. Once the circuitry pattern is imprinted, the wafer has to be charged.
These machines use a lot of energy to produce electrical charge that allows the electrical to flow to the chip and also creates the different type of function for your electrical chips.
Rajkumar says many of these steps are repeated hundreds of times before the fabrication is complete. And to get to this point, these orders have to be made at least a year in advance.
I have a demo wafers here.
The finished wafers are tested, then finally sliced into individual chips.
One is the small die wafers, which is mainly used for bank cards or chips. And then you have the other one, which is the bigger die wafers, which can go into other kind of applications like computer processing chips or electrical appliances.
Global Foundries says its fab in Singapore typically makes about 600,000 wafers a year. But with the recent surge in demand, it's making around 120,000 more.
This whole year is fully booked up. We don't have any more space for new customers.
Tan Yu Kwong is the Vice President and General Manager of Global Foundries Fab 7 in Singapore, and he says there's no quick solution.
There's no space that you can house another lithography tool or any other tools that you like to buy. It is the lead time easily a 1 year to 15 months. Before you can CO2 that is coming into your factory.
It's not just a backlog of equipment, but Tan says expanding or building a fab from the ground up would require deep investments, more than the $1.4 billion that GlobalFoundries has already committed to spend this year on expanding its 3 fabs around the world.
You easily need to spend 7 billion to 15 billion, depending on the size of the factory you want to build, and the technology that you're going to develop can easily take you.
Professor, is it okay to leave class now?
I'm sorry?
Is it okay to leave class now?
Yeah, go ahead. Sorry, I lost track of time, so feel free to jump off if you want to.
All right. Have a good evening, Professor.
Bye.
Fill as many orders as quickly as possible, the company turned on idle machines and opened this factory control tower. Engineers here have a bird's eye view of the entire fab, and the green boxes show which machines are running at max capacity. Before this control tower, when there was a problem, engineers had to sort through data and piece together information themselves.
Compared to today, just looking at the screen, you already know that this is a piece of machine. You need to pay attention now.
Tan says any time saved is precious, but to truly address the shortage, the company is working more closely with its clients, suppliers, and the government.
We're going to continue seeing more government support because it is becoming such an important part of the entire global supply chain.
There's no reason why America should wait. We're investing aggressively in areas like semiconductors and batteries.
The Biden administration has proposed $50 billion to boost America's chip production. That's because while the US is one of the largest semiconductor markets, the majority of the complex and expensive manufacturing happens at a few companies based in China and East Asia.
That's because the world's biggest foundry in the world, TSMC, is located in Taiwan. Samsung also has a sizable foundry as well as some Chinese players.
This concentration of fabs means any disruption to the supply chain, like a drought in Taiwan or political tensions with China, can have big ripple effects, especially when global demand is expected to grow by more than 12% this year.
We have technologies like 5G and artificial intelligence, and these types of advanced technology means that more chips will be needed to operate the devices that we use every day.
To meet that demand, the Chip Industry Association says it will require an investment of $3 trillion globally over the next 3 decades. So for us to buy new devices, Tan says his fab will work around the clock as it turns this challenge into a business opportunity.
From the ambitions of wanting to grow the company, this is definitely a positive point for us. This over demand is going to be around for a while.
Okay, guys, sorry to keep you, but hopefully that gives you an idea about sort of the overall market and what the end thing is that you're going to be building if you get into microelectronics. Anyway, I'll let you guys go at that. On Thursday, we're kind of start getting into the meat of the class. We're looking at semiconductors, how they work, and how we can modify it. Okay, guys, take care.
Thank you.
Bye. Thanks.
Thank you. Oh,
Professor, I had a question.
Yeah.
I was looking at the files tab on Canvas, and there's this PDF called One Slide Deck 1, but it says it's not available because it's part of an unpublished module.
Ew.
Was that supposed to be the notes?
Yeah, that was supposed to be the notes. Sorry, I guess I'm still trying to figure out how to deal with Canvas, so I'll dig into that. It wasn't, it didn't have anything, we didn't get into that today, but I'll need to fix it for next lecture.
Okay.
Next for Thursday. Thanks for letting me know.
No problem. Thank you.
Thanks.